Hello, my name is Michael Gottesman, and I'm a compiler engineer at Apple working on the Swift programming language. Today, I'm going to present Ownership SSA, an extension of SSA that embeds ownership information into a mid-level IR. Before we begin, let's set out a quick roadmap. First, we will explore the history of the development of automatic reference counting, or ARC, in Objective-C and Swift, and how ARC emission evolved from manual reference counting. Then, we will look at the limitations of this approach caused by its usage of intrinsics that cannot express ownership information known by the front end, resulting in this information being lost. Then, we're going to look at how Ownership SSA, or OSSA, enables this information to be modeled and preserved in an IR. And finally, I'm going to more formally define OSSA and show how it can be applied to implement various language semantics. By the end of this talk, you should have a better idea of why formulating an IR that captures and validates the high-level ownership intent expressed by the programmer instead of the low-level implementation details allows for a more correct compiler implementation that emits better code gen. All right, let's get started by talking a little bit about manual reference counting and ARC's development from it. Manual reference counting is a form of garbage collection that requires the programmer to manually manage an object's lifetime by incrementing and decrementing an integer reference count to track the number of references to the object. Because reference counting has a low runtime and memory footprint when compared with other GC methods, reference counting is often used to implement GC in a systems programming context. As such, manual reference counting is used in non-ARC Objective-C, the internals of CPython, the Linux kernel, the XNU kernel, and more. In order to maintain correctness, these approaches define conventions for what operations are required where when taking or giving up ownership of an object. Let's take a quick look at an example of manual reference counting. In this snippet, we are invoking some constructor of the class list, returning the instance already retained from the constructor, and then binding that instance to X, casting X to collection, binding the result of this cast to Y, sorting Y, and then finally releasing X, destroying the class. This example lowers as follows into an IR modeled on Swift's intermediate language. Given that the user manually expressed these operations, the lowering is pretty much a one-to-one translation between code and instructions. Of course, humans managing object lifetimes like this doesn't scale well due to programmer error. For instance, nothing stops me from using X after I've released it, resulting in a runtime crash due to a use after free. And if I forget to release X, then I just silently introduced a leak. Over time, the prevalence of leaks and use after frees and manual reference counted code led us to realize that this bug-prone task needed to be automated in order to improve overall system correctness. Thus, Clang introduced Objective-C automatic reference counting, or ARC, to automate these conventions at the language level. Clang implemented managed lifetimes automatically by inserting intrinsics that lowered to those same runtime calls previously invoked manually by the programmer. That's why I call this form of ARC intrinsics-based ARC. As expected, this automation did eliminate common sources of leaks and use after frees by just leaving ownership to the compiler instead of to the user. But there was a performance cost, since codegenning an AST via a standard AST traversal doesn't yield the same global ownership knowledge that our original manual reference counting programmer had. Thus, in order to maintain performance, optimizations that removed ARC operations were introduced. These types of arc optimizations require the optimizer to reconstruct global ownership information by semantically interpreting the emitted IR. Over time, we found that inferring such semantics was difficult and pretty bug-prone. To see this, let's go back to our original example and convert it to arc. First, converting our source on the left to arc. Notice how this resulted in our user being able to eliminate that final release from their source, which is totally awesome. But let's see how this conversion changes our code gen. Notice how since the front end is tracking the lifetimes of X and Y separately, our example now has an extra retain and release that was not in the code gen of our original example. When Objective-C Arc was initially worked on, we saw tons of code patterns like this and realized that we needed to ensure that we could eliminate unneeded, balanced retain-release calls if we wanted to be able to get near to the performance of manual reference counting. This required the optimizer to have to interpret this soup of retains and releases and attempt to reconstruct from scratch the ownership information that was already known by the front end. We found that such semantic interpretation was easily defeated by standard compiler optimizations, resulting in the optimizer instead approximating this ownership information. The simplicity and obvious correctness of these optimizations led us to conclude that the actual problem here were not those optimizations, but rather the ability of the IR to express and statically maintain high-level ownership information. To see how this lack of expressivity in practice result in information loss, let's break down the semantic steps in our example and then apply one simple optimization. First, we construct X. Then, we copy X and bind it to Y by calling retain to increment the reference count of X. Then we take Y and cast it to collection. Then we sort Y. And finally, we destroy our variables, destroying first Y and then X. Given this example, we only need one standard optimization to introduce multiple semantic program interpretations, namely passing %0 instead of %1 to release. This is a legal optimization, since casting Y to collection is only needed to call sort, not to release Y. And the underlying pointers, %0 and %1, are exactly the same. This results in the IR no longer expressing which release explicitly destroys Y, resulting in this code now being able to be semantically interpreted in multiple ways. Of course, our intended semantics is one of the possible interpretations of this code. We could interpret the inner retain and cast as a fused copy-cast operation of X that was split into two instructions by the front end. This would imply that Y is an independent copy of X with its own live range. But since there isn't a release explicitly on Y, statically, we don't know where the live range of Y actually ends, and have to assume that there's some sort of obfuscated balancing release later in the emitted code. This would force the optimizer to classify this retain of Y as conservatively not balanced and not remove our inner retain release. Or we could interpret that initial retain as not being part of the definition of Y at all, and instead interpret Y as an unsafe, non-reference counted pointer to X without its own lifetime or semantic live range. This would imply that we are treating X as a base value for this unsafe operation, requiring us to emit a defensive copy of X into its separate binding Z for the duration of that unsafe call. This then implies that an optimizer could potentially eliminate our inner retain release calls since they balance each other and they seem rather unneeded. But in truth, this obvious transformation is in fact unsafe, since we could have that our retain and release are actually balanced by obfuscated release-retain operations in our magic ellipses. In such a case, if we did remove our retain release calls, we would have miscompiled the code and introduced a use after free, causing the program to crash when executing the remaining retain. This is an example of a real miscompile that was exposed by real customer code that we fixed by making the optimizer more conservative. So let's go back over the forms of information loss in the previous example, but this time using words. Retain-release relationships were not expressed in the IR and could not be recovered. This was seen by each previous example having different interpretations of which retains and releases balanced each other, all from the exact same IR. This lack of knowledge around which retains and releases balanced each other then resulted in different interpretations of the individual live ranges of values. Without further information, we could not infer if Y was an independent copy of X or just some non-reference counted pointer to X. As such, any IR emitted by intrinsics-based ARC has multiple, potentially correct, static ownership interpretations. And finally, this information loss resulted in the front-end and optimizer attempting to conservatively approximate each other's semantics, incorrectly sometimes, to prevent miscompiles like the one I showed you previously. These types of miscompiles were not good for users. So after some discussion and thought, we began to investigate other approaches that could express this lost information, leading us eventually to Ownership SSA. Ownership SSA is a modification of a typical SSA IR model that imbues def use edges with static semantic ownership information. Edge endpoints are required to have compatible ownership semantics. This is a two-way relationship that both requires that the def semantics can be accepted by a given use, and also that a given use's semantics can accept that def. Importantly, these rules are statically verifiable at compile time by the IR verifier, so the compiler writer can insert with confidence that all code that is in OSSA maintains these invariants from code generation until this information is lowered later in the compilation pipeline. And finally, this IR model defines a static contract in between the front end and the optimizer to prevent these sorts of semantic approximation bugs that I mentioned before, allowing for both the front end and the optimizer to be more expressive and correct. All right, let's go back to our original example and convert it to OSSA. Notice how in the OSSA version of this code, all operations that produce a new def by constructing or copying an object like X on the first line have results that are explicitly used by balancing destroy operations like our destroy on the last line. This property is enforced by the static verifier at compile time. So if we did not actually destroy X, the IR verifier would look at %0 and see that %0 did not have any direct users that destroyed it, and then emit a nice diagnostic saying that X was leaked. In contrast, in our non-OSSA example, we would just silently leak. This relationship in between defs and uses is the basis for capturing ownership information in OSSA. Now, let's take a deeper, more formal look at this relationship. In OSSA, all defs have a statically assigned ownership kind that specifies the ownership semantics that the def models. All uses of a def must be able to be semantically partitioned in between normal uses that just require liveness and consuming uses that end the lifetime of the def and after which the object can no longer be used. Since consuming uses end a def's lifetime, we naturally must have that consuming uses jointly post-dominate all other uses, and that a def must be consumed exactly once along all program paths, preventing leaks and use after freeze. To see this in more detail, let's bring back our example and consider the uses of X. Notice how we first create a def for x. We then use x in a non-consuming manner to produce y. And finally, destroy x, consuming the value. This partition of x's uses into consuming and non-consuming uses allows us to conclude unambiguously that we have only one possible semantic interpretation here, specifically that x must remain alive until the end of the example. In fact, since ownership is expressed on function arguments as well, we can do a completely local analysis to prove globally that x is not leaked or overconsumed. If we try to pass x to an escaping consuming function, the IR verifier will treat our last destroy as a use after free, keeping us honest. The semantics of x in the previous example is one form of ownership semantics supported by OSSA, namely own semantics. In OSSA, we actually support 3 different types of semantics, and thus have 3 different ownership kinds. First, we have non-ownership. This is used to represent values that do not require memory management, like inert plain old data values, such as an integer or a float. 2, owned ownership. A value with owned ownership is a value that exists independently of any other value and is consumed exactly once along all paths through the program. In our previous example, x and y were objects with owned ownership. And 3, guaranteed ownership. A value with guaranteed ownership is a value with a scoped lifetime whose liveness is dependent on the lifetime of some other base value. With our remaining time together, we're going to look at owned and guaranteed ownership, talk in depth about their properties, and show what a front end could implement on top of them. Let's talk a bit about owned values now. Owned values and owned ownership is a form of ownership that models move-only values. We require that our value is consumed exactly once along all program paths. The IR verifier will flag at compile time values that are not consumed along a path as a leak and any double consumes as use after freeze. Move operations are modeled via forwarding uses such as cast or fee nodes that take an owned value as input, consume that owned value, and then produce a new semantically independent owned value as a result. And finally, we use owned values in OSSA to break down complex ARC def use graphs into a series of simpler direct copies and forwarding uses. To show how an ARC object's def use graph is broken down, let's go back to our OSSA example and break down y's def use graph like we did for x's. First, notice that the def use graph of y is different than x's due to the introduction of a forwarding cast. Specifically, we define y by copying x, then we pass y to our forwarding cast, which consumes y and forwards y into a new owned value z. This forwarding is our move operation. And finally, at the end of the code snippet, z is consumed, ending the underlying object lifetime originally created by y's def. Importantly, this implies that if at the end of scope we were to destroy y instead of z, we would have violated OSSA form, and the IR verifier would nicely catch for us that we violated move semantics by omitting 2 diagnostics. First, that we used y after it was consumed, and second, that z was leaked since it was never consumed. Now that we understand what owned objects are, let's look at how one can work with subfields of an owned object. Let's assume I have an app about pets, where I aggregate business information about my user into a user struct. This struct has 2 reference-counted fields, one that represents state about the pet, and a second that contains the user's payment information. We want to pass off our payment info to the function payBill. Since user is owned, we know that it can be consumed only once. This suggests that if we want to access parts of user without creating additional owned values by copying user or its contents, we must consume user in some way and forward its ownership into its constituent parts. This is done by using a destructure operation. A destructure operation breaks down its input argument into the argument subcomponents, forwarding the input argument's ownership semantics into each individual subcomponent. This necessarily also requires us to split up the destructure of %0 into two different destroyed. What if we then want to use our user struct again? Well, then we have to reform the user struct from its constituent parts, combining our destroys once more. And then, if we want to access the payment info again for a different reason, we have to destructure again. As one can see from this example, even though reasonable in the small as a way to extract fields from a struct, on a larger scale, using destructure in this manner results in IR bloat. But luckily for us, we can use guaranteed ownership semantics to access the underlying fields of our user without consuming the underlying value. Guaranteed ownership in OSSA is used to model values that have a scoped, dependent lifetime on a base value. As such, guaranteed values are never consumed since the scope provides liveness via that dependence on the base value. These scopes are introduced into the IR by explicit begin and scope instructions. These instructions summarize explicitly the regions of code where the guaranteed value can be used, resulting in simplified analysis and verification. A base value, regardless if it is owned or guaranteed, must statically be live until the end of the scoped region. This ensures that our base value is never invalidated while our guaranteed value is live. And finally, values with guaranteed ownership follow a data flow rule that states that any forwarding uses of the guaranteed value are also guaranteed and are recursively validated as being in the original value scope. This was a choice that we made to reduce idempotent scopes in the IR. All right, let's go back to our previous example. Again, we just want to pass off only payment info to the function payBill. We could use destructures, but that would involve us having to bloat the IR. So instead, let's use our new knowledge of guaranteed ownership. First, notice that we are introducing a few new instructions here, begin guaranteed and end guaranteed. These are the begin and end scope instructions that define and summarize our region of access to our base value, %0. By creating this scope, we are asserting in an easily verifiable manner that over the entire scope, %0 will not be destroyed, meaning we can access its internal state safely without worry. Additionally, due to our recursive data flow property, we don't need to reborrow the result of the field extract before we pass it to payBill. And in fact, if we want to reuse this value multiple times, like in our bloated destructure example, we can just pass different guaranteed references to the inner state of the value, yielding the following IR. Doesn't that just look nicer in terms of lines of code? But even more importantly than this brevity, we can now code gen with confidence. Since if we were to destroy a user in the guaranteed region, we would get a nice diagnostic from the IR verifier telling us that we are destroying an own value before its last normal use, the end scope. Guaranteed ownership has many more uses beyond safely using subfields of own values that I'd like to highlight, but given that we only have a couple of minutes left, I would like to speak about one of those uses, modeling safe interior pointer values. In code, sometimes one wants to be able to use a pointer that provides access to the internal state of an object. This is called an interior pointer, since the validity of the pointer depends on the base object remaining alive at all uses of the interior pointer. Returning such interior pointers is generally unsafe in C-like languages since one doesn't have a non-manual manner to guarantee that the base object stays alive. For instance, in the following small example, we are using std vector data to access the interior pointer of a vector after the vector has been deallocated. OSSA provides a few ways to access safe interior pointer values. For our discussion today, I'm going to speak only about one, direct accesses to interior pointer values. Let's take a quick look at an example of such an access. In this example, we are accessing an inner pointer of the class, and loading from that pointer. In order to ensure that all such uses are within a guaranteed scope, we require that instructions like field pointer ref only accept operands that have guaranteed ownership. By doing this, we ensure that our usage of inner pointers are always statically verified as being within a guaranteed scope allowing the optimizer to avoid needing to recursively visit all interior pointer uses to determine if the base value of the interior pointer is still valid. Since we are providing that guarantee, if we use the own value %0 directly, immediately at compile time, the IR verifier would nicely statically flag our error with a diagnostic. And if we were to load from our interior pointer outside of the guaranteed value scope by mistake, the IR verifier would again keep us honest and emit a nice diagnostic saying that we used our interior pointer outside of the guaranteed value scope. All right, let's do a quick recap. 1. OSSA expresses ownership semantics lost by intrinsics-based art by representing and capturing ownership in the IR. By embedding into an IR a static ownership model that captures the actual programmer's intent instead of these low-level implementation details, more high-level constructs are exposed, allowing for the IR to be unambiguously semantically interpreted, and also prevents abstraction leaks. By enforcing this model statically, OSSA allows for improved compiler correctness by allowing for ownership verification throughout the compilation pipeline. This then results in improved front-end and optimizer correctness, and most importantly, improved front-end expressivity and optimizer performance. Thank you very much.
We have time for a couple questions.
Hi, question. So this is good for the IR, and I see that's like really analyzable and great. Do you think that should percolate up into the source language that the programmer writes?
Well, this is actually solving a different problem than that. What this is, it's not actually trying to catch use after freeze emitted by the programmer. So it's actually solving a completely different problem. I definitely think that finding use after freeze and leaks in user code is amazing, but that's not what the problem here that we're trying to solve. The problem we're trying to solve here is making it so that the optimizer in the entire compilation pipeline can avoid those mistakes. And the front end, yeah, that's how I would say that.
So at some point, the ownership SSA gets lowered down to the traditional retain and releases. And is your recommendation that we write optimizations at the ownership level so that we don't get it wrong?
Yes.
Or is there still optimizations that work after lowering? And what about them? Do we have some way of enforcing the correctness?
Yes. I would say that all ownership optimizations should be done on OSSA. Period. It embeds the semantics. You're not trying to approximate any, you're dealing exactly with the actual material you're trying to work with. Why work with plastic if you really need to be working with steel?
Hi, not a question, but a testament to the last point. So we worked on a transformation on OSSA that was previously not using OSSA, and that led to many benefits due to the verification. So it's really what you want to be working with.
So my colleague here was talking about, this is from the TensorFlow for Swift project, where they moved their transformation onto OSSA, and they were having huge problems with leaks, which was a giant pain in the butt for them to track down. And immediately, in like 1 or 2 weeks, they had one engineer who was able to statically track down all of the leaks that were from their transformation code, because you don't have to actually take out your sanitize or anything. Literally, this just tells you immediately, compiler engineer, you made a mistake here, and you made a mistake here, and you made a mistake here, and this is why you made that mistake. And so it just makes dealing with these errors quick and easy and light. That's how I would put it.
Exactly, thank you. Any upfront verification errors are certainly much better than having to debug it via instrumentation or some other mechanism.
Yeah.
So it pays dividends.
All right, I think that's all the time we have for questions, so let's thank the speaker.